Yes. Good morning, students. My name is Shankar, chemistry faculty for IIT JEE and NEET exams, competitive exams like IIT JEE, mains, advanced, and NEET exam. So today we are going to discuss few examples on SN1 reaction and SN2 reaction. Few examples on SN1 and SN2 reaction. So we'll start. So in SN1 reaction, we are going to discuss few examples. See, there are a few examples. So this is one of the nucleophilic substitution reaction through SN1 condition. See, in SN1 reaction, we know SN1 reaction involves or SN1 reaction proceeds through two steps. Two steps are present in SN1 reaction. In step 1, breakage of carbon halogen bond and form carbocation. So in step 1, breaking of carbon halogen bond and the formation of carbocation. This carbocation, so SN1 reaction was two steps. So in step 1, formation of carbocation, and the step 2 is the generally attack of nucleophile on the carbocation which is formed in the step 1. So here the nucleophile is generally, in this case, if you observe here in this reaction, so here leaving group is Cl minus ion and incoming nucleophile is OH minus ion. So here Lg indicates leaving group, Nu indicates nucleophile, that is specifically incoming nucleophile. So leaving group is chloride ion, incoming nucleophile is OH minus ion. So actually, generally nucleophile attacks on the carbocation, but in this example, so if you observe here, this is what? Secondary carbocation. Before attack of a nucleophile, here there is a possibility to undergo carbocation rearrangement to increase the stability of carbocation. So here carbocation rearrangement occurs. By hydride shift. Here you will find one hydrogen. So this hydride will shift to here. So this is the newly formed carbocation. So if you observe this one, this is tertiary carbocation. This is the tertiary carbocation. When compared with the secondary carbocation, we know tertiary carbocation is more stable. So before attack of nucleophile, So secondary carbocation is converted into tertiary carbocation through this carbocation rearrangement. And then next, attack of nucleophile. And then next, attack of nucleophile. So here, whatever lone pair of oxygen present in the water attacks on the carbocation, because it acts as an electrophile, this species will act as a nucleophile. So this is how nucleophile attacks on the tertiary carbocation. Further, by loss of proton, so finally, so you are going to get this product. Finally, you are going to get this 6-membered ring. So this is the 6-membered ring product you are going to get. So this is the one, actually the product. So through this mechanism, so SN1 reaction takes place. Okay. So this is the one example of SN1. We will see the energy diagram also. So we will see the energy diagram also. So energy diagram I will explain in the next page. So if you observe the energy diagram, energy reaction coordinate. So in this example, the energy diagram looks like. So this is the reactant. This is the reactant. This is the product. So in this example, so sorry, I want to change small things. So this is the product. So see, in the previous example, how the energy diagram occurs. So if you observe, so this is the reactant. So this stage is called secondary carbocation. So this point is called tertiary carbocation. So this stage is secondary carbocation. This point is tertiary carbocation, and then finally it is giving product. Because of presence of carbocation rearrangement, so the energy diagram appearing like this. If there is no carbocation rearrangement, generally the SN1 reaction will stop up to this stage. At this stage. So here carbocation and then attack of nucleophile, and you are going to get the product. Because of carbocation rearrangement possibly is here, so the graph appears like this. So this is about energy diagram of the previous example. Now we'll go to further few examples. So see. SN1 condition. I am taking this example as a SN1 condition. So we will go through the mechanism. We will go through the mechanism so that you will get clear idea. So in step one, so cleavage of carbon halogen bond. So you are going to get the carbocation. So in step one, you are going to get the carbocation by the cleavage of carbon halogen bond. Next one, see. Next one, if you observe this one, in this example, there is a possibility to undergo ring expansion. There is a possibility to undergo ring expansion. So for our convenience, I am giving the numbering. So this is I am considering the first carbon, second carbon, third, fourth, fifth, sixth carbon. So bond break takes place between 2 and 6 as per this numbering way. So now when bond pair electrons are shifted towards sixth carbon, so you are going to get 6-membered ring by the new bond formation between one carbon and sixth carbon. New bond formation between first carbon and sixth carbon. So then you are going to get a 6-membered ring. You are going to get a 6-membered ring. Sorry. You are going to get the 6-membered ring. I am giving the numbering for convenient. 1, 2, 3, 4, 5, 6. See, new bond is formed between first carbon and sixth carbon. And when this bond pair electron shifted towards sixth carbon, on second carbon, you are going to get positive charge. You are going to get positive charge. And first carbon, who is there? Methyl is there. And first carbon, so methyl is there. So this is the ring expansion. So this is the ring expansion. We know, so 6-membered ring is more stable than 5-membered ring in this case. And then, so here see, there is a possibility to undergo carbocation rearrangement. So this is the secondary carbocation. This is the secondary carbocation. So because of hydride shift, so here carbocation rearrangement. So carbocation, so when this hydride, when the hydrogen present at this carbon, when this hydrogen shift to this carbon as a hydride form, so you are going to get tertiary carbocation. CH3. So this is how. So this is how secondary carbocation further converted into tertiary carbocation. And then finally, so next one is the attack of nucleophile. So here you are going to get the molecule like this, CH3 OH2 plus, and then finally loss of proton minus H plus. So this is our product. This is our product. This is how a few examples of SN1 reaction involves ring expansion and then carbocation rearrangement. So this is the one most important example of SN1 reaction which involves many steps. Okay. Next we will go to another one more example. We will go to one more example. So we know generally in SN1 reaction, if there is a possibility of stereochemistry, we are going to get a racemic mixture. But remember, so racemic mixture means 50% of R isomer, 50% of S isomer, but it is not actual 50%. So 2 to 5%, up to 5% of opposite isomer. 2 to 5%, instead of 5%. 5% of inversion configuration is the higher level. Inversion configuration is the higher level when compared with the retention configuration, because at the initial stage, leaving group is present in the substrate. So at the initial stage, incoming nucleophile attacks from the backside of the stereocarbon, means backside of the chiral carbon. So when at the initial stage, when incoming nucleophile attacks on the backside, so automatically inversion product will be higher level up to 5% in few examples. Okay, we'll see. So this example I am taking under SN1 condition. So under SN1 condition, we know, so this is the chiral carbon. So this is the chiral carbon. So you will find the racemic mixture. So this is the racemic mixture we are going to get. This is the racemic mixture we are going to get under SN1 condition. Okay, if you take some other examples. So if you take this example, so here you are going to get the diastereomeric product. Here you are going to get the diastereomeric product. How I will see. How we'll see how it takes place. So we know in step one, cleavage of carbon halogen bond and then formation of carbocation. So here you are going to get so in step one, so carbon halogen bond broken and then formation of carbocation. So if you observe this one, if you observe this one, here see this molecule contain two chiral center. See, after formation of carbocation, one chiral center. This chiral center is fixed. There is no change. There is no change in the configuration of this chiral center during this reaction. So we know carbocation having empty p orbital. The empty p orbital, to this empty p orbital, nucleophile can approach from either front side direction or back side direction. So when nucleophile attacks from front side of the p orbital on the back side of the p orbital, then only we are going to get racemic mixture. So front side attacks OH here, back side attack OH backside. So here also this carbocation having empty p orbital, so incoming nucleophile can attack from front side and back side. But here one chiral center is fixed. So because of this reason, you are going to get diastereomers. One chiral center is changing, other chiral center there is no change. So the relation between these two is diastereomers. The relation between these two products is diastereomer because configuration at one chiral center, no change. See, deuterium at the right side, here also right side, here also right side. We know to get anisomers, so configuration at all chiral center must be opposite. So because of this reason, the relation between these two is diastereomers. So in this reaction, you are going to get diastereomeric products. Two products, those are diastereomers to each other. So we will go to one more example. Okay. Something will take. Say hydrogen ethyl. See this example. If you see this example, the difference between the previous example, this one. So same concept. I am placing nucleophile under SN1 condition. Under SN1 condition, how it proceeds? So here you are going to get four stereoisomers. Four stereoisomers. Four stereoisomers. Stereoisomers. For stereoisomers as a product, we will see. In step 1, we know breaking of carbon halogen bond. So here you are going to get carbocation. Here there is a formation of carbocation. So if you observe here, this is the secondary carbocation. So when this carbocation, by carbocation rearrangement, if the positive charge is shifted to this carbon, you are going to get more stable carbocation, benzyl carbocation possibility is there. So because of this phenyl carbon resonance, carbocation stability increases. So it undergoes carbocation rearrangement. It undergo carbocation rearrangement by the hydride shift. So this hydride will shift to here. So here you are going to get carbocation. Here it is ethyl. Here it is phenyl. Sorry. Then phenyl. Next, for our correct example, I want to change small thing. So I want to change small thing. I am placing some different group to get the, as per our example, expecting. So here you are going to get deuterium hydrogen methyl. Okay. So this is how carbocation rearrangement to increase the stability of carbocation. And then if you observe next step 2, attack of water molecule. See here. So when water molecule attacks, so I am writing the normal way. So here I am writing CETOH. Next here it is phenyl. Here you are going to get a C DH-methyl. So in this example, here you are going to get 4 stereoisomers because observe the product, here the molecule contain 2 chiral centers. 2 chiral centers. 2 chiral center with different terminals. 2 chiral center with different terminals. Then number of stereoisomers equal to number of stereoisomers equal to, we know, 2 power n. So here it is n equal to 2 because 2 chiral centers are present in the carbon. So then you are going to get 4 products. Then you are going to get 4 stereoisomers as product. 4 stereoisomers as product. So because of why in the previous example we got 2 diastereomers, in this example we got 4 stereoisomers because here both chiral centers proceeds through carbocation possibility. Here carbocation formation takes place. When carbocation formation takes place, here there is a possibility to form 2 diastereomers, and then further nucleophile attacks. So nucleophile can attack from where? Front side and back side. Here also same hydride can attack from where? Front side, back side. Here also OH minus can attack from front side, back side. So totally all possibilities, by considering all possibilities. So here this is the product. In this product, how many chiral centers are there? 2 chiral centers. So this is the chiral center. This is the chiral center, or this is the one more chiral center. So total 2 chiral center. When 2 chiral centers with the different terminals, number of stereoisomers equal to 4. So 4 stereoisomers as product. In this reaction, totally you are going to get 4 stereoisomers as a products. Okay, na? So this is how it is different from previous example. In this example, we got 2 products. Those are diastereomers to one each other. They are related by diastereomic relation. When you go to here, total 4 products. What is the configuration? What will be the configuration of those products? Can you say? So configuration can be RR, next can be SS, next can be RS, next can be SR. So 2 chiral centers. With the 2 chiral centers, these are the 4 configuration possible. These are the 4 configurations possible: RR, SS, RS, SR. So we know these 2 can be called as a enantiomers. These 2 can be called as a enantiomers. These 2 are enantiomers, those 2 are enantiomers. Other combinations are diastereomers. So this is how SN1 reaction contain many examples with the different stereochemistry. Okay, thank you.